Okay, hello everyone. My name is Fei Long, today's presenter for this paper. Unfortunately, the first author of this work, Tianfeng Liu, is not here, is unable to be here today to present this research in person. I will present this work on behalf of the entire author group. The name of this work is CCEval, a framework to accurately and confidently evaluate performance matrix of congestion control algorithms for data center networks. This work is a joint effort with researchers from ZGC Lab, the Chinese University of Hong Kong, Shenzhen, Beijing University of Post and Telecommunications, and the University of Pennsylvania. So congestion control in data center networks has long been an extreme active research area. With the rapid rise of data-intensive applications, especially distributed training and serving for LLMs, and the demand for efficient low latency and congestion control. To meet this demand, researchers have proposed numerous high-performance CCAs over these years. Seminal works like DCTP from CCOM 2010, pFabric, Timely, DCQCN, HPCC, and many more. With all these new algorithms being proposed, new CCAs must be evaluated fairly against existing state-of-the-art solutions. Most importantly, researchers need to be confident that the performance results they report are representative across real-world deployment environments and robust to the inherent randomness of data center workloads. So to understand where the gap is, let's first walk through the standard CCA evaluation workflow that nearly all existing workflow follows. So this workflow has three core steps. First, generate the experimental configuration. This includes defining the workload, network topology, and specific CCA parameters for the test. Second, execute the CCA experiment. Researchers sample a traffic workload as a single trial and run multiple trials to form a complete evaluation. And third and finally, estimate the key performance matrix. This includes calculating core metrics like flow completion time, their quantities, and applying the chosen estimation methodology. So we asked, how is the confidence in recent CCA evaluation? We surveyed 20 high-cited CCA papers in data center networks from CCOM, NSDI, ATC, and EuroSys in recent years. So for each paper, we look at two things. Did the authors report a margin of error around their reported metric? And did they report how many trials they ran? We have two key findings. First, most papers fail to report margin of error and trial count. And second, among the reported work, most papers use a very small number of trials, only 5 or 10. And to validate the impact of these practices, we conduct experiments to show the impact of variability in experimental results. Based on the experimental results, we have two key observations. The first observation is that due to the system variance, variability of FCD quantile is inevitable and enlarged independent of the number of trials. The standard deviation ranges up to 50% of the mean value. So the second observation is that limited trial counts leads to low confidence and misleading conclusions for both large and small flows. So in the large flows with only 10 trials, HPCC is larger than DCQCN. However, after 500 trials, the conclusion flips. HPCC is smaller than DCQCN. In the small flows with only 10 trials, Timely is 6 times larger than DCQCN. But after 500 trials, Timely is only 50% larger than DCQCN. Clearly, these observations undermine the entire foundation of fair CCA evaluation. So to achieve accurate and confidence estimation in CCA evaluation, we propose CCEval. CCEval contains 3 key designs. First, CCEval uses the confidence interval CI to quantify the accuracy and the confidence of estimation for researchers. Second, CCEval proposed a model-free quantile estimation algorithm, which forecasts the trial count for achieve a given confidence interval and generalize to any CCAs. Third, CCEval proposed a model-based tail quantile estimation algorithm, which reduced the necessary trail count without sacrificing accuracy and confidence. The workflow of CCEval consists of two inputs, including the experimental configuration and the estimation configuration. And the output of CCEval is the confidence interval of interested performance metric and the corresponding trail count. So first, let's cover the core statistical foundation of CCEval, estimation using confidence intervals. From a random variable z with unknown parameters theta, a random interval I rho is a confidence interval with confidence level 1 minus rho, if and only if the probability of theta in range of theta 1 and theta 2 is 1 minus rho. For example, in this plot, if we set the confidence level at 95%, which means that the estimation value has 95% chance laying in the random interval, the half width is the accuracy of CI, or the error between real and estimated error. Estimated value, okay. So we deep dive how CCEval construct the confidence interval. We find the CCA evaluation workflow obey the IID assumption. Each trail comes from identical distribution and is independent with each other. Hence, we can use the Monte Carlo method, and based on the central limit theorem, the empirical mean approximated by normal distribution. Hence, we can first compute the empirical mean. Then we compute the empirical variance, and combine them, the confidence interval is shown. So based on the above logic, we propose a model-free performance estimation algorithm. The goal is to construct a confidence interval with given relative error and confidence interval, confidence level. The algorithm consists of two stages. The first stage is exploratory stage. We could run at least n trials to calculate the interval empirical mean and variance. The second stage is the production stage. We should run more trials and update empirical mean and variance until meeting the convergence condition. Based on the convergence condition, the algorithm convergence rate is square root of n. Hence, the required trial NE can be estimated by the following equation. This equation telling them how long the experiments will take. So while the model-free algorithm is universally applicable and extremely robust, it has one key limit for extreme tail quantiles, which is crucial for applications like LLM serving. Tail quantile estimation needs massive trials to achieve high confidence and high accurate, and may unaffordable for researchers. To overcome this question, we propose a model-based tail quantile estimation. The key idea is that we use importance sampling to increase the probability of tail event. This algorithm consists of 5 logical parts. First, we model the input and output distribution. Second, we use regenerative method to calculate tail probability. Third, we use importance sampling to improve the tail quantile estimation. Fourth, we use cross-entropy method to search near optimal IS distribution. At last, we use model-free algorithm to generate the confidence interval. So we first describe the input and output distribution. We model service time Sn as a logarithmic normal distribution, while inter-arrival time follows an exponential distribution. For the output, we model response time Rn. Response time includes the network RTT time, transmission time, and the queuing time, which are influenced by the congestion control algorithm. So we make the tail probability estimation based on the regenerative process. We treat multiple trails as a regenerative process. During one trail, the network becomes busy and evolves according to the workload and the congestion control behavior. When a new trail starts, the network is restarted, so the process regenerates. Hence, we can estimate the tail probability and tail quantile based on the renewal reward theorem as shown in this equation. We further improve the tail probability estimation with importance sampling. This method uses another distribution called IS distribution. This distribution will make the rare event gamma occurs more often. As a simple example, the brown line is the new IS distribution. This makes the gamma event occurs more often. Since we changed the distribution, we need also change the expectation E based on the IS distribution and the likelihood ratio L. At last, the remaining question is how to choose a good IS distribution. We use adaptive cross-entropy method to minimize the KL divergence between the original distribution and the IS distribution. So after using this method, we have the following optimization problem. And this problem, it has one unique global maximum and a closed form solution. Now I will move to the evaluation. We evaluate CCEval in both simulation and a real-world testbed. We use web search flow distribution, fat tree topology in simulation, and a dumbbell topology in the real-world testbed. The target algorithms include DCTCP, DCQCN, HPCC, and timely. Unless otherwise stated, we use a 95% confidence level and a 1% relative error target for the confidence interval. So the first question is whether CCEval can evaluate performance matrix accurately and confidently. So on the factory topology, CCEval calculates confidence intervals for both the 5th percentile flow completion time of large flows and the 99.9th percentile flow completion time for small flows. So the result shows that the real confidence interval quickly converges and satisfies the required accuracy. So we also tested whether CCEval works across different network simulators. Besides NS3, we evaluate M3 and Parsimon. CCEval is orthogonal to the simulator because it only relies on the samples produced by the repeated trials. The results shows that it can calculate accurate confidence interval across all three simulators. We also observe that M3 and Parsimon may produce distributions that differs from NS3, partially because machine learning-based simulators can introduce biased estimation. So next, we evaluate the trial counting forecasting. CCEval forecasts the required trial count accurately for different quantiles, while with forecasting errors roughly between 1% and 10%. The result also revealed two useful insights. First, more than 25 trials are usually used to converge to a small relative error such as 1%. And second, the required trial count increased significantly as we move toward more extreme tail quantiles. This matches the intuition. Tail matrices are harder to estimate because informative samples appear less frequently. So this slide tests generalization to a different network topology. Here, CCEval evaluates the 5th percentile flow completion time of large flows and the 99.9th percentile flows completion time of small flows on the dumbbell topology. We then move from simulation to a hardware testbed. The testbed uses the same dumbbell topology as the NS3 simulation. CCEval still calculates the correct confidence intervals for different quantiles, and the required trial count increases from the median to the 99.9th percentile. However, the real-world testbed needs more trial than simulation. This is expected because operating systems, hardware, and background effects introduce additional variability. So another important factor is traffic duration. CCEval can calculate confidence intervals with the required relative accuracy across different duration settings, but duration changes the meaning and quantile and the quality of the samples. So the first insight is that very short experiments may contain many non-representative flows. So the resulting confidence interval can describe in the wrong performance distribution. And the second insight about duration is the opposite extreme. Very long trials may require more total flow samples and longer runtime before the confidence interval converges to the desired relative accuracy. So therefore, researchers should not choose trial duration arbitrarily. The practical goal is to find the minimal duration that still produces a correct and representative estimation. So now we evaluate the benefit of the model-based tail quantile algorithm. Compared with the model-free approach, it reduces the trial by 75% to 80%. The reduction comes from two sources. First, CCEval model the flow size distribution accurately. Second, important sampling increases the chance of observing tail events. Together, these techniques make high tail evaluation much more efficient. So to conclude, we find that existing congestion control evaluation workflow often fail to provide enough statistical confidence for performance metrics. And CCEval addresses this problem in three ways. It uses confidence intervals to quantify accuracy and confidence. It provides a model-free estimation algorithm that generalizes across congestion control algorithms. It further designs a model-based tail quantile estimation algorithm to reduce the required trails without losing accuracy. Overall, CCEval achieves 1% relative error and 95% confidence, and will be open sourced for the community. That's all of the presentation. Thanks everyone for listening. Any questions on CCEval, please mail to the following address. Thank you very much for your attention.